encoding. We
Hmm.
defined sampling. We also understood what is the use of sampling, sir.
Ah, okay. Then what about quantization? I didn't discuss.
Yes, sir.
I discussed about
Quantization.
quantization also, no?
Yes, sir.
Uniform and non-uniform in that A law, mu law and all. I think I showed the graphs of that, right?
Yes, sir. Yes, sir.
Uh, then why people should not forget, na? Okay.
Yes, sir.
So I think everyday study is must for this. As I said, you will be doing experiments in the next semester lab. Okay. So it is very important and interesting also. Okay. So I hope just I will run through the slides. The things what I discussed yesterday. Okay. Yeah, it started from this slide. What I feel, right. So I said basically in PCM the message signal will be represented as a sequence of coded pulses. Right. I said how do we achieve that sequence of coded pulses? That we achieve by representing the signal in discrete form, that is both in time and as well as amplitude, right? So the basic operations performed in the transmitter of the PCM are what? Sampling, quantizing and encoding. These are the three key operations performed at the transmitter of the pulse code modulation. Fine, I shown this is the block diagram of uh, PCM, right? I said this is my analog input signal. So these three blocks, sampling, quantizing, encoding, are known as the PCM encoder. So when I sample it, the signal becomes discrete in time, right? Then I said this should be what horizontal slicings, right? This should be like this, I said. Okay, so this is the quantization what I'm saying. Then by encoding each of the quantized level with binary information, I get the digital data. Fine. Then, yeah, as an example, I've shown this. So this is my analog input signal. When I sample it, this is the analog signal, right? And the thick vertical lines are the sample values, and then dashed lines are the representation levels, right? Horizontal, this one. This is how those three operations are done. Okay. Yeah, and I took this example and I have shown complete process of PCM. Okay, this example is more than enough for you to understand PCM. How do I convert the analog signal into a digital one? Right? I said PCM is nothing but analog to digital converter. So it involves three processes, that is sampling, quantizing, and encoding. Right? So here this is my analog signal, and the dotted lines are the rounded off sample values. Right? I divided my input signal into 8 levels. That is, I represent that by 0 to 7. Right? Means I have maximum of plus 4 volts and minimum of minus 4 volt. So I said no. So what I have done here, quantized value between minus 0.5 to 0.5, I'm taking it as means what I mean to say is the levels starting from say minus 3.5 to 2.5. Right? Means these are my quantized values, isn't it? So as I said here, MK, then MK plus 1, in between value, I will be taking that as my VK. That is the quantized value, right? Hope getting my point. How I am getting this quantized value? That is starting from minus 3.5, minus 2.5, right? Then minus 1.5, minus 0.5, 0.5, 1.5, 2.5, and 3.5. So these are my quantized values. I am representing each of these quantized values by a binary number. So here I represent the decimal number, that is from 0 to 7. I can code that to binary equivalent, right? Yes, is this point is clear? So yesterday I discussed very well. So with respect to this, this is the first sample value, right? That is minus 0.2, and this one is what, 0.1, right? And this one is minus 1.1, and this is I think, zero point 0.8, and this value is 0 0.6, and this value is minus 0 0.8, this sample value is minus 0 0.9, and this sample value is minus 0.2, and this sample value is 2.6, right? So this is a sample value what I have shown now. Then the quantized value, what? The sampled value will be rounded off to the nearest quantized level. That is, this will be rounded off to minus 0.5. So 0.2 is rounded off to minus 0.5. Then 0.1, next is 0.1, right? That will be rounded off to 0.5. Okay, 0.1 will be rounded off to the quantity level 0.5. Okay, then minus 1.1 sample value will be rounded off to minus 1.5 quantity value. Okay, then next is the 0.8 is my sample value, that will be rounded off to 0.5. Okay, so like that it is done for all other sample values, and these are the quantity values. Okay, then based on this I am rating what is the level number. So that is for minus 0.5, my level number is 3, right? Then for 0.5, my level number is 4. Like that I have written for each of these quantity levels. Then I am writing its equivalent binary code, right? For 3 it is 011, for 4 it is 100, for 2 it is 010, like that, right? Then these 011, 100, these things will be represented by some form of binary pulse. Okay, so that we'll discuss today. So what are the different types of binary pulses we can use to represent this binary number? Okay, so similar to that, I took some more examples. This is another one. Then, yeah, here I have shown with respect to the binary equivalent and its waveform. Okay, yeah, this is another example what I have shown. One more example. So like 4 or 5 examples I have taken, and even I told what is the application. Where do I use this analog to digital converter, right? Some 2-3 applications I said. One is in CD, MP3, internet telephony, right? I said it is basically used in telephone, right? With the what data rate, right? So I said our voice signal frequency range, I said it is from 300 Hertz to 3400 Hertz. It will be rounded off to 4 kilohertz. That is why it is sampled at 8 kilohertz. Okay, that is the Nyquist criteria, right? Then each sample value will be represented with 8 bits. That is why 8 into 8. So you will get 64. Right. So 64 kbps is the data rate for a voice signal over the telephone line. Okay, 64 kbps in that way. This is the bandwidth required for transmitting our voice over the telephone line. Okay, similarly for other this one, for CD it is 1.4 or 11 Mbps I said. For MP3 different data rates are achieved, 96, 128 and 160. Then for internet telephone it is 5.3 kbps and above. Fine. Then I think yeah, this is all fine. Why we use low pass filter before sampling, right? And all I discussed. Then yeah, this is the block diagram of the PCM system I said, right? So this is my analog input signal. Then I pass that signal through a low pass filter. Then I do sampling, quantizing, then encoding. Then I get the digital data, that is PCM. So this is just regenerative repeaters. We'll see what is there inside the regenerative repeater in upcoming classes, right? Then I said about the receiver, right? Decoder, reconstruction filter, and as well as the destination. So this is a complete PCM system. And yeah, this already discussed about sampling, right? Yes, I was telling about this quantization. Here I said for voice, we use non-uniform quantizer because our voice voltage range means we talk sometimes loudly and we talk sometimes with low pitch. So that variation will be is in the order of 1000 to 1. So in case of non-uniform quantizer, what is going to be done? The representation levels, the spacing between the representation levels is not uniform, right? So we represent with a different step size. For low amplitude levels are represented by small step size, and the high amplitude levels are represented by large step size. So with that, we say there will be variations in the step size, right? Yeah, I was talking about that, and then I said the two types of non-uniform quantizers are there. So one is the mu law, another one is the A law, right? So these are the compression techniques which we use, right? And we express the mu law mathematically like this, right? So V is equal to log of 1 plus mu into mod of m divided by log of 1 plus mu. So what is that? V is the output voltage and M is the normalized input voltage, and mu is the constant, right? And I hope I have shown the graph of mu law for different values of mu. So when mu is equal to 0 is what? When mu is equal to some other values also. I said when mu is equal to 0, it will be uniform quantizer. It corresponds to uniform quantizer, right? So I think, yeah, this is the graph, right? When mu is equal to 0, so it is a uniform quantizer because this is the input and it is the input versus output graph, right? So output increases linearly with the variation of the input voltage, right? And these two values, when mu is equal to 5 and mu is equal to 100, so there will be some bending of this curve, right? This is not linear. Means so this becomes non-uniform. Okay, mu is equal to 5 and maximum value of mu is 100. Okay, which is used in systems. So here there is this bending. This indicates that there is a non-uniform spacing of representation levels. That one. Okay, so I was talking about this, right? Yeah, fine. This is the expression for V, for mu law. Means it is a logarithmic scale that we need to understand. Then, yeah. See, for given value of mu, the reciprocal slope of the compression curve, right, that will define the step size, right? And the derivative of m with respect to v will be this, d by this log of 1 plus mu divided by mu into 1 plus mu into mod of m. So, as I said, this mu law is neither strictly linear nor strictly logarithmic. Okay. Why I am saying this is neither strictly linear nor strictly logarithmic? Because it is approximately linear at low input levels, corresponding to the value of this, that is mu into mod of m, much less than 1. And it is approximately logarithmic at high input levels, which corresponds to mu into mod of m is much greater than 1. Okay. Fine. Yeah, already repeated. Then another compression law is the what? A law. Okay. Another compression technique is the what? A law we say. So how do we define that A law is with this? So this is the output voltage, right? Normalized output voltage, which is equal to A into mod of m divided by 1 plus log A when the value of m is less than or equal to 1 by A and greater than 0. And when the value of m lies between this, means when it is less than 1 and greater than 1 by A, so this is the expression for output voltage. That is 1 plus log of A into mod of m divided by 1 plus log A. So you need to understand these equations. So these are the logarithmic equations, right? So the practical values of A, okay? As I said, it is 100, right? So here, in case of mu law, when mu is equal to 0, it was uniform quantization, we said. But in case of A law, we say when A is equal to 1, okay? When A is equal to 1, that corresponds to uniform quantization. When A is equal to 1, okay? Similarly, the reciprocal slope of this compression curve is given by the derivative of that, so which is shown here, d by d of m by d of p, which is equal to 1 plus log A by A over this range, and it will be 1 plus log A into mod m over this range. Okay. Yeah, here the step size, okay, over the central linear segment will have a dominant effect on small signals and are dimensioned by the factor A by 1 plus log A. A divided by 1 plus log A. So this is about around 25 dB as compared with the uniform quantization. So let me show the graph of that also, A law. Hope you understand this. This is for A law. So when A is equal to 1, it becomes a uniform quantization because it is linearly varying, means output is linearly varies with the input. For different values of A, I hope we will be able to see that the bending of curve, right, means it indicates non-linear. Okay. So I said maximum value of A used is 100. Okay. Yeah, so that is all about A law and mu law. Many times they ask about these two things. I think you should be able to draw the graph for different values of mu and different values of A, and you should be able to write those expressions. Okay. So how we get those equations is behind the scope of our discussion, because we are not going to derive any of those expressions. You need to understand how can we write that. So I think so. This is about the yeah, in continuation of that only. So to restore the signal samples to the correct relative levels, right? So we need to have a device in the receiver which will have the complementary characteristics of the compressor. Fine. In order to restore the signal samples to their corrective relative level, we must, of course, use a device in the receiver which will have the characteristics complementary to the compressor, right? So such device is known as the expander. So we do compression at the transmitter side. We need to do the expansion in the receiver side. In a simple word to say. Okay, the compression and expansion laws are exactly inverse, isn't it? Because except for the effect of quantization. Okay. The expander output is equal to what? The compressor input. So why we compress and send the signal? To minimize the bandwidth, right? At the receiver side, again we need to do the reverse operation, that is known as the expander. So the combination of compressor and the expander is known as the compander. So in one word, we say it is a compander. Means if I use compressor at the transmitter side and expander at the receiver side, the combination of that is known as what? Compander. Okay, what he says is in actual PCM systems, the compounding circuitry does not produce an exact replica of the nonlinear compression. Okay, what we were discussing, what we have shown in the curve, right? So it provides piecewise linear approximation to the desired curve. Okay, so with that, so by using large enough number of linear segments, the approximation can approach the two compression curve very closely. Okay. Yeah. Yes, this is all about quantization. That's whatever we have discussed so far. After quantization, the next step is encoding, right? So let me have a discussion about this. Okay, so encoding, what I said, that binary digits will be encoded by some of the waveforms, right? So in combining the process of sampling and quantizing, the specification of a continuous message signal becomes limited to discrete set of values. Means here I am telling the importance of sampling and quantizing, right? So by doing so, what I am saying is the baseband signal becomes limited to a discrete set of values. Okay. But whatever the discrete set of values I get after doing this sampling and quantization, that may not be suitable straight away for the transmission over the radio path or the transmission line. Okay, so to exploit the advantages of the sampling and quantizing, right, for the purpose of making the transmitted signal more robust to noise, interference, and other channel degradations, we need to we need to look upon the use of an encoding process to translate that discrete set of sample values to a more appropriate form of the signal. Okay. Fine. So with the sampling and quantizing, as I said, the message signal, which is continuous in time, right, becomes limited to discrete set of values. So whatever the discrete set of values I get, that may not be straight away best suitable for transmission over the line or radio path. So to exploit the advantages of this sampling and quantization, I need to make use of those advantages for the purpose of transmitting the signal over the line or radio path, which should be robust to noise, interference, and as well as the channel degradations. So for that, I need to think of what should be the best encoding process I can use to translate this discrete set of samples into a more appropriate form of the signal. Means here, what I want to stress upon is there are a variety of line coding techniques or encoding techniques. Among that, we need to choose the best one. Okay, so let me discuss about those line coding techniques. Then you will understand. Okay, among that, that depend upon the application, which line coding will be used for what applications. Okay, so any plan for representing each of these discrete set of values as a particular arrangement of discrete events, we call that as a code. Okay, line code we say na. So here, what is that code means? This one. Any plan of representing each of those discrete set of values as a particular arrangement of discrete events means yes, you will understand the meaning of this when I take up the example. Okay, so one of the discrete events in the code is known as the code element or the symbol. Okay, means the discrete events means what? It may be the presence or absence of the pulse, that we call it as a symbol. Okay, presence or absence of a pulse is known as a symbol, right? So a particular arrangement of symbols used in the code to represent the single value of the discrete set is known as the code word, or we call it as a character. Okay, then in binary code, okay, each symbol may be either of two distinct values, right, such as presence or absence of the pulse. So two symbols of the binary code are denoted as 0 and 1. This you already known very well. Hope you are clear with the definitions. What is code? What is code element? Right. Then what is symbol? Then what is code word or character and all? Hope, is it clear? Yes, let me take an example, then it becomes. Similar to the binary code, even we can have a ternary code also. Means in case of ternary code, each symbol will have one of the three distinct values. Right? Ternary means it is 3. In case of binary, only 2 levels, 0 or 1. Right? In case of ternary, I can have 3 different amplitude levels. Right? So the maximum advantage over the effects of noise in the transmission medium is obtained by using the binary code, okay, rather than any other form of the code. That is why binary code is preferred. Okay, so this binary symbol will withstand relatively high level of noise, and it is very easy to regenerate also. Okay, so we may use different codes other than binary, but binary code have the advantage of what? It is more robust to noise and it is easy to generate. That is why we all stick on to binary code. So in case of binary code, right, each code word consists of R bits. Okay, each code word consists of R bits. Then, so you know what is bit, right? It's a binary digit. So that R denotes the number of bits per sample. Okay. So R denotes what? Number of bits per sample, right? So with that, whatever I said now, binary code can represent total of 2 power R distinct numbers, right? Means if I use it, if the value of R is 3, right, means I will be able to have a total 8 combination of pulses, okay, right? So where R is what? Number of bits per sample, right? So if I take R is equal to 3, means 2 power 3 is 8. So here he has given the example of the value of R is 8. Okay. So when it is R is 8, 2 power 8 is what? 256 levels we get, right? That we call it as a 8-bit code word. Okay. Other than that, there are several ways of establishing this one-to-one correspondence between the representation levels and as well as the code words. So the convenient method is to express this ordinal number of the representation level as a binary number. So in case of binary number system, each digit has a place value. We all know that that is power of 2, right? So 2 power 0, 2 power 1, 2 power 2, 2 power 3, 2 power 4 and all, right? So with the 4 bits per sample, when R is equal to 4, I think here I have a table which will show you the different binary numbers. Hope you are understanding this. This is when R is equal to 4. Okay. So these are, we say, representation levels, that is from 0 to 15. That is 16 levels are there. Right. So for 0, I can represent that by 4 zeros. Isn't it? So 2 power 4 is 16, right? So 16 levels I can represent 0, 1, 2, 3, 4, and so on up to 15. Yes, is this clear? Yes, is this clear? See, if I keep saying these things theoretically, you may not, right? But when I show this table, you will be able to understand quickly, okay, what I am saying. Okay, I think this, being in fifth semester, you should be able to understand binary, decimal to binary, right? So let me have a discussion about the line codes, what I was telling now. How do we represent these representation levels in the form of pulses, right? So that is what the line code is. Okay, so in line code, the binary stream of data, right? Binary stream of data will be represented as our electrical representation, right? So line codes, we have two things. One is non-return to zero, that we call it as NRZ, non-return to zero. Another one is return to zero, that is RZ we say. Non-return to zero, and another one is return to zero. Okay, so the line code is what? It is basically used to represent the binary stream of data by an electrical pulse. Okay, so in case of return to zero, what happens? The pulse shape, whatever we use to represent the bit, always returns to the 0 volts or the neutral level before end of that bit. That is known as return to zero. Hope understanding my point. Return to zero means what? Whatever the pulse shape we use to represent the bit, okay, always it will return back to 0 volts before the end of the this one. Yes, hope getting my point. Line code is what? It is an electrical representation of a binary stream of data, right? I said in line code we have two terminologies we use. That is, one is non-return to zero, another one is return to zero. What I said, what is return to zero? So return to zero means what? The pulse shape, whatever I use to represent the bit, always returns to 0 volts, right, before the end of that bit. Before the end of that bit, I will show you the example. Then non-return to zero means whatever the pulse I use to represent the bit will not return to zero. Okay, it does not necessarily return to zero before the end of the bit. That is why it is called as non-return to zero. Means it can occupy the entire bit duration in case of non-return to zero. In case of return to zero, before end of the bit duration, it will come back to zero. That is the return to zero. Okay. Yeah. So this is one example which I have taken. So this is my binary data 0, 11, 0, 1, 11, 0, 1. Okay. So this is my binary data. How do I represent this with the different types of line codes? So I have not yet told what is the first one. I will come back to this diagram first, saying what are the different types of line codes. Okay, so totally we will be discussing 5 different types of line codes. Yeah, I will just name here. Okay, so one is unipolar non-return to zero. Even we can have unipolar return to zero also. Okay, fine. Unipolar non-return to zero, then unipolar return to zero. Similarly, next one is polar signal we say. So here unipolar, polar is important. Unipolar means, I will tell what it is, unipolar. Okay, in that again two cases, NRZ, RZ. Unipolar non-return to zero, unipolar return to zero. Similarly, next one is polar. In that again I can say two things. One is polar non-return to zero, then polar return to zero. Next one is bipolar. Okay, in that again I can say bipolar non-return to zero, bipolar return to zero. Then the last one is the split phase or it is known as Manchester code. Okay, so these are the 5, means actually 5 types: unipolar, polar, then bipolar, then Manchester. How many? 1, 2, 3, 4. Okay, out of 4, in these 3, that is in case of unipolar, in case of polar, and in case of bipolar, I can write two things, that is NRZ and return to zero. So 3 into 2 is totally 6. Plus this is 1. 7 times I can write totally. Okay. So first let us see what is unipolar non-return to zero signaling. Okay. I will go here. Yeah, this is the unipolar. Uni means what? What do you mean by uni? It is single, right? Means it has single polarity. Means 0 will be represented by no pulse. Okay, I am representing 0 by no pulse. 1 will be represented by a pulse. So this is my 1. Okay, here I have 2 ones now continuously. That is why I am, so if I consider this is my bit duration, so T suffix B indicates bit duration, right? So here 2 ones I have, so I am representing 1 by a pulse having magnitude of plus A volts. Okay, 2 ones. Next 0 is there, so there is no pulse, so I represent with the 0 level only. Then again 1 is there, so I represent that 1 by a pulse having a magnitude of plus A volts. Okay, the next 2 zeros are there, I represent with no pulse. The next 1 is there, I represent that by a pulse having a magnitude of A volts. Hope this is clear. This is what? Unipolar non-return to zero. Unipolar okay, unipolar NRZ. NRZ means what I said, non-return to zero, right? Means it will not come back to zero even at the end of the bit pulse. There is a non-return to zero, means it will occupy the entire bit duration in the same state. If it is zero, it will be at the zero level only. And if it is 1, it will be at one level only. It need not come back to 0. Okay. Yes, this point is clear, I hope. The next one is there, that is why return is 1. Right, next 0 is there, so it is represented by 0 for the complete duration. Next 1 is there, so return 1. The next two zeros are there, the 0 level, then this one. So similarly, if I want to write unipolar return to 0, same thing, unipolar return to 0, I can write it as what? So unipolar means it has only one polarity, okay? Here 0, binary data 0 will be represented by no pulse, means it is at 0 volts. Binary data 1 will be represented by a pulse having certain bit duration with a magnitude of plus a volts. Okay, so it is non-return to 0 means it occupies the entire bit duration. Okay, 0 will be having this much and then 1 will be having this much. Okay, so in case of unipolar return to 0 means 0 will be represented by no pulse, it will be as it is. So now it is 1 now. In case of return to 0, what happens? It will be high for half of the bit duration, then it will come back to 0. Okay, it will be high, means it will be plus a volts for half of the bit duration, and it will come back to 0 and will be staying at 0 for another half of the bit duration. Again, next one is there. Again, it will go back to high. Okay, it will be high for half of the bit duration. Again, it will come back to 0. Okay, so 0 by no pulse, same thing. Then here 1 is there, no? So it will be high for half of the bit duration and again it will come back to 0. So that's why it is called return to 0. Okay, so 0 in represented with no pulse. The next bit is 1, so it will be high for half the bit duration, again it will come back to 0. So this duration, no? So till this it will be TB, right? Till this it will be TB. So it will be high only for half of the bit duration. Only this time, means this duration it will be high. Another half of the bit duration it will be low. Hope my point is clear for return to 0. Yes, my dear students, should tell. Have you understood this return to 0 or non return to 0? Yes?
Yes, sir.
So return to 0 means what? In case of unipolar return to 0, right? First we need to understand what is unipolar. Unipolar means it will have only one polarity. Okay, I represent the binary information with only one polarity. Right, so 0 I represent with no pulse. 1 will be represented by a pulse having a magnitude of a volts. Okay, this A may be anything. It may be 5 volts or 3 volts or 10 volts, anything, right? That is why in general I am writing A volts. So in case of non-return to 0, the binary bit 1 will be occupying the entire bit duration, TB. Okay, if the bit duration is TB, it will be I for the entire bit duration. Okay, right? That is why it is not come back to 0 here. That is why it is shown 2 at high only for 2 binary ones. Then 0 by no pulse. That is why it has come back to 0. Then 1, it will be at high for a bit duration of TB. Like that. Okay. In case of return to 0, what happens? I said, in case of unipolar return to 0, 0 will be represented by no pulse. 1 will be represented by a pulse. Here, what happens? It will be, means binary data 1 will have an amplitude of A only for half of the bit duration. Okay, another half of the bit duration will come back to 0. Here, so 0 to this TB is by bit duration, right? Only half of the bit duration will be high. Another half of the bit duration will come back to 0. Hope I am clear. Yes, is this my point is clear? Hello. Yes, people should say yes or no. Is this clear? In case of return to 0, binary bit 0 will be represented by no pulse. Binary bit 1 will be represented by a pulse having a magnitude of A, right? And that magnitude of A will be there only for half of the bit duration. Another half of the bit duration, it comes back to 0. That is why it is called return to 0. Okay. Yes, is this clear? ಏನು ಹೇಳಲ್ರಿ? Yes or no? Yes.
Yes, sir.
Okay, thank you. Yeah, so this one, next one is polar. Okay, this one is a polar non-return to 0 signaling. Okay, so polar means it will in polar signaling we represent 0 binary information 0 by a negative amplitude minus a volts. Okay, and binary data 1 will be represented by a positive pulse having a magnitude of plus a volts. That is why here see first bit is 0 now, so it is represented by minus a volts. The next bit is 1, so that is why it is represented by plus a volts. Right? Same, the bit duration will be same, TB only. The next bit is also 1, that is why it is represented by plus a volts only. And then next bit is what? 0, right? That is why that is represented by minus a volts. Okay, this one. The next bit is 1, so that will be represented by plus a volts. Then next two bits are 0, right? So that is why those two will be represented by minus a volts. Minus a volts. Okay. Then next is 1, so that will be represented by plus a volts. Right? Is that fine? Yes, I was telling about polar. No, this is polar non-return to 0. In case of polar, I said binary data 0 will be represented by what? A negative pulse having a magnitude of minus a volts. And the binary data 1 will be represented by a positive pulse having a magnitude of plus a volts. Okay, so that is why here it is negative pulse for the first bit, right? The next two bits are 1 1, so it is represented by positive pulses. The next bit is again 0, it is represented by a negative pulse having a magnitude of minus a volts. Again, next bit is 1, so it is represented by a pulse having a magnitude of plus a volts. Right? Then next two bits are 0 0, so it is represented by two negative pulses having a magnitude of minus a volts. So next bit is 1, so it is represented by a pulse having a positive amplitude of plus a volts. So this is polar non-return to 0. If I want to write polar return to 0, hope this point is clear. This is whatever I have shown right as of now, it is polar NRZ. Non-return to 0 means I said it will be occupying the entire bit duration. Okay. If I want to say, if I want to write this polar return to 0 for the same sequence, so what I will be doing, it will be means binary data 0 will be represented by a negative pulse only for what? Half of the bit duration. Okay, so it will be minus a volts only for half of the bit duration. Then it comes to 0. Okay, so this bit duration will be what? TB by 2. Okay, another TB by 2 will be 0. So next what 1 is there, right? So here this is the entire bit duration, right? Right. So it will be plus a volts only for half the bit duration. So another half the bit duration, it comes back to 0. It will be like this. Again, next bit is 1. So again it will go back to high. Okay, and again it will be high for another half the bit duration. Again it will come back to 0. Like this. Hope understanding what I am saying. Then next bit is 0. So it will be negative for only half of the bit duration. then it comes back to 0. So this is polar return to 0. Okay, then you can write this also like that. 1 will be like this. Okay, the next bit is 0, no? So it will be minus A volts only for half the bit duration. Another half the bit duration will be 0. Then again it will be minus A volts only for half the bit duration. Then another half the bit duration will be 0, like this. Okay. So for 1 also it will be plus A volts for half the bit duration. Another half the bit duration it will be 0. So you should write like this for polar return to 0. Okay, whatever I have done, it is for polar return to 0. Polar return to 0. Okay. So whatever is drawn is that is for polar NRZ. Hope this point is clear. I repeat once again, in case of unipolar signaling, 0 will be represented by no pulse, 1 will be represented by a positive pulse. Okay, that you have to be very clear. NRZ and RZ. NRZ means it will not return back to 0. Return to 0 means it will be returning back to 0 before the end of the bit. Means here what I have taken is it will be high for only half the bit duration. For another half the bit duration, it comes back to 0. I am sure, right? So in case of polar, I said binary information 0, binary bit 0 will be represented by a negative pulse, and binary 1, binary data 1 will be represented by a positive pulse. Okay, so that is NRZ. Then polar return to 0 means, so it will be means for binary data 0, it will be a negative pulse only for half of the bit duration. It comes back to 0 for another half of the bit duration. Okay, for positive means for binary 1, it will be a positive pulse only for half of the bit duration. Again, it comes back to 0 for another half of the bit duration. Okay. Okay, then let us see what is the next one is bipolar. Okay, bipolar is slightly tricky. I will tell what is that bipolar. Okay, of course, here he has shown C is your unipolar. Hope you will be able to understand this. This is unipolar. Okay, unipolar return to 0 means this is for 0, then this is for 1. So it is only high for half the bit duration, and it will be low again for another half the bit duration. Okay, so I don't want to repeat again and again. It is fine. So this is my bipolar signaling. So we need to understand in what way bipolar is different from other things. In case of bipolar, what we do is 0 will be represented by no pulse only. Okay. 1, okay, will be represented by alternate positive negative pulses. Okay, 1 will be represented by what? Alternate positive negative pulses. I will show with respect to the sequence. Yeah. Yes, what I was telling in case of bipolar, I said alternate ones will be represented by positive negative pulses. Okay, so here 0 represented by no pulse. Here first one will be represented by a positive pulse, right? The next one will be represented by a negative pulse. So that keeps repeating. Hope getting my point. The first one, so I said 0 in case of bipolar, 0 will be represented by no pulse. Then 1 will be represented by, means alternate ones will be represented by alternate positive negative pulses. The first one will be represented by a positive pulse, right? This one, and next one will be represented by a negative pulse. Next 0 by no pulse. The next one is come. One has come, right? So this one will be represented by a positive pulse because previous to this one has come. Now that will be represented negative pulse, right? So here the ones what I wanted to say in simple words. The binary data 1 will be represented by alternate positive negative pulses. Hope this point is clear. The binary data 1 will be represented by alternate positive negative pulses. Means with respect to this to say first bit is binary 0, data is 0, so I represent with no pulse. Next bit is 1, I represent with positive pulse. Next bit is 1, I represent with what? Negative pulse. Again, next bit is what? 0, I represent with no pulse. Next one will be represented by positive pulse because the previous one was represented with negative pulse. Next two zeros are there, so no pulse. Next one is there, right? So this will be represented by a negative pulse. Hope this point is clear. This is bipolar. That is why it is called bipolar. Means it has two types of polarity. Bi means what? Two, right? Bipolar means I will be representing the binary data 0 by no pulse and binary data 1 with the two polarities. Okay, positive and negative pulses. So each line code has its own advantage and disadvantage. I will just say, but you should be able to understand now how can I represent these different types of line coding techniques. So this is the last one, that is Manchester code we say. Manchester, or it is known as a split phase. So here what happens is binary data 0 one minute. Yeah. Yeah, in case of split phase or Manchester code, 0 will be represented by what means here half of the bit duration will be negative pulse, then another half the bit duration will be a positive pulse. Okay, that is known, that is why it is called split phase. Okay, half of the bit duration it will be a negative pulse and another half the bit duration it will be a positive pulse. That is for binary data 0. Then for binary data 1 it will be half of the bit duration will be positive pulse, then another half the bit duration will be a negative pulse. Okay, half of the bit duration it will be a positive pulse, then another half the bit duration will be represented by a negative pulse. Hope this point is clear. See, binary data 0 will be represented by what? A negative pulse for half the bit duration, and another half the bit duration will be represented by a positive pulse. Then binary data 1 will be represented by what? Half of the bit duration by positive pulse, and then another half the bit duration by negative pulse. So like that, similarly for next one is there. So it will be high for half the bit duration, then again it will be low for another half the bit duration. The next bit is 0, so it will be 0 for half the bit duration, then again it will be high for another half the bit duration. Fine. So next bit is 1, so it will be high for half the bit duration, again it will be low for another half the bit duration. Okay, so till this. Fine. So next bit is 0, so it will be low for half the bit duration, again it will be high for another half the bit duration. Then next bit is 0, so it will be low for half the bit duration, another half the bit duration will be high. Fine. The next bit is 1, so it will be high for half the bit duration, again there will be low for another half the bit duration. Means in every bit duration there will be a transition from negative pulse to positive pulse or positive pulse to negative pulse depending upon the binary data. So it has its own advantages. I will discuss that I think in the next class. Okay. So far I discussed just how to represent the given binary data with these different types of line codes. Okay, so with this, let me stop.